Welcome to the second part of the problem solving session 1 on Introduction to Hydrological Processes for the NPTEL course Surface Water Hydrology. It is an NPTEL online certification course for free and is being taken by Professor Dr. Rajiv Maiti from the Department of Civil Engineering, IIT Kharagpur. I am the teaching assistant Aman Srivastava and I am currently enrolled for solving numerical problems concerning each topics being taken every week. So, based on the week 1 lectures being taken by Professor Rajiv, we will be focusing towards solving further problems. So in the last part of this video, we focused on solving problems on residence time. In this session, we are focused on solving numerical problem related to water budget equation. So here is the first problem. Let's discuss this problem. Estimate the constant withdrawal rate from 1375 hectare reservoir in a month of 30 days, during which the reservoir level dropped by 92 centimeter, despite an average inflow into the reservoir of 0.5 million meter cube per day. During the month, the average seepage loss from the reservoir was 2.5 centimeter. The total precipitation on the reservoir was 18.5 centimeter. And the total evaporation was 9.5 centimeters. So this was the first part of the problem, where the objective is to find out the constant withdrawal rate from the reservoir. The area of the reservoir is given to us. The duration of 30 days is also given to us. Apart from this, we found that there is a drop in the reservoir level. That means the volume of water has reduced in the reservoir, and the depth of fall in the reservoir level is 92 centimeter. Apart from this, we are also provided with the inflow rate with which the reservoir is being recharged, and the rate is given here 0.5 millimeter cube per day, and this rate has been continued for the 30 days time. Also, some other hydrological processes such as seepage loss, precipitation and evaporation depths are provided to us. In the second part of the problem here, keeping conditions the same, what will be the constant withdrawal rate if the reservoir level drops by 73 centimeter? So, if we see, there are two parts in this problem. First part focuses on if the drop in the reservoir level is by 92 centimeter, and the second part, what will be the constant withdrawal rate if the fall is 73 centimeter. So we see that we need to find out the constant withdrawal rate for two different cases, where in the first case, the drop in the reservoir level is 92 centimeter, and in the second case, the drop in the reservoir level is 73 centimeter. So let's see how the withdrawal rate gets influenced due to different falls in the reservoir depths. Okay, so here is the summarization of whatever conditions that has been provided in the problem. The area of reservoir is given to us 1375 hectare, and it has been converted in million meter square, that is 13.75 millimeter square. The duration of 30 days has been given to us. We have kept the unit of time in this problem as days only. Drop in reservoir depth is given to us in centimeter. We have converted it into meters. Average inflow rate was given to us million meter cube per day. So we were interested to find out what is actually happening for the entire duration. So the duration is 30 days. So we have multiplied the average inflow rate with the duration. So 0.5 into 30 it gives us 15 millimeter cube. This is the volume of the water which has been inflowed into the reservoir. Likewise, we have seepage depth which is given to us 2.5 centimeters. So we were interested to find out the volume of seepage loss which has occurred from the reservoir. So we have multiplied this 2.5 centimeter with the area of reservoir, which is 1375, and it gives us 0.025. Okay. So here we have simply converted the depth from centimeter to meter, and we can eventually estimate the volume of seepage while solving the problem. Whereas here in the precipitation depth, centimeter was given to us 18.5, and it has been converted into 0.185 meter. Likewise, evaporation depth of 9.5 centimeter has been converted as 0.095 meter. So these are the things, these are the conditions which were provided in the problem, and these are the converted magnitudes of the conditions which were provided. So we will be focusing solving this problem using these magnitudes in these units only. Okay, so let's solve the first part of this problem, where the fall in the magnitude was 92 centimeters. So reservoir level dropped by 92 centimeters is the first case. So there are several steps to follow for solving this problem, and altogether our aim is to realize like how the water budget equation is coming to picture and is helping us to actually identify the constant withdrawal rate from this reservoir. In the step 1, we will be finding the total input volume. So to find out this total input volume, we need to consider on two aspects. First is precipitation volume and another is the inflow volume. So these are the two attributes which actually contributes to the input of the total volume of the reservoir. So this reservoir is receiving additional water from precipitation and through inflow. So let's try to quantify these two attributes. Here we see that the depth of the precipitation was 18.5 centimeter. It has been converted into meter. Likewise, this precipitation depth has been multiplied with the area of the reservoir. We see that the area of reservoir was given as 1375 hectare. So this hectare has been converted into meter square by multiplying it with 10,000, and it has been subsequently divided by 1 lakh, 1 tens, 100, 1000, 10,000, lakh, 10 lakh. So it is actually the million. So we are dividing it by 1 million to get the total area of the reservoir as million meter square. So multiplying this area of reservoir in million meter square with the depth of precipitation in meter, it yields the precipitation volume of 0.5 millimeter cube per day. And accordingly, we have also estimated the inflow volume, which is 0.5 millimeter cube per day into 30 days. So we have seen in the previous table as well, like how these conditions were actually given to us and how we are converting their units for convenience for easy calculation. So if we solve this part, we get the total precipitation volume as 2.54 millimeter cube, and likewise if we solve this part, we get the inflow volume as 15 millimeter cube. So adding together, we get 17.54 millimeter cube as the total input volume. I hope you were able to follow the step 1, where we were interested to find out how much is the volume of water which is provided as input to the reservoir system. Moving ahead, let's move to step 2, where now we are interested to find out the total output volume. So how much is the amount of water which is being taken away or taken out from the reservoir system. To find out this total output, we need to focus on seepage volume and evaporation volume. We see that from the reservoir, these are the two attributes based on the problem which has been provided to us, which is actually taking out the water which is stored in the reservoir. So seepage is one of the process from where the water is leaking out from the system, and evaporation is another process where the water is evaporating back into the atmosphere. So these are the two conditions where the amount of water is being taken out from the reservoir system. So now let's try to quantify these two processes. Seepage depth was provided to us in centimeter, which has been converted into meter as this, and it has been subsequently multiplied with the area of reservoir. Likewise, the evaporation depth was also given to us in centimeter, which has been converted into meter as this, and it has been multiplied with the area of reservoir. So why we are multiplying it with area of reservoir? Because we wanted to find out the seepage volume and evaporation volume, and volume SI unit is in meter cube, right? So we were actually provided with seepage depth and evaporation depth in the problem, but we are also provided with the area of reservoir. So multiplying the area of reservoir with the depth of seepage and depth of evaporation will yield the volume of seepage and volume of evaporation. So by solving these equations, you will get the seepage volume as 0.34 millimeter cube and evaporation volume as 1.31 millimeter cube. Adding together, we get the total output volume of 1.65 million meter cube. I hope you were able to follow, and I also request all the viewers to also try solving this problem by using calculator and also by using pen paper for better clarification. Moving ahead, let's look at the step 3, where we are interested to find out the change in the storage volume. So in order to find out the change in the storage volume, one aspect which was provided in the problem was the drop in the reservoir volume. So let's try to quantify the drop in the reservoir volume. Firstly, since there is a word drop which indicates that there is a decrease in the volume of the water in the reservoir. So technically we will be putting a minus sign in this equation. So this minus sign is indicative of that the water volume from the reservoir is declining, and that's why this minus sign is required at this point. And we also know that the 92 centimeter was the drop in the water depth, and we have converted it into meter. And like we have seen in step 1 and step 2, in step 3 also we are multiplying the depth of fall in the reservoir level with the area of the reservoir in order to get the volume of drop, and it comes out as minus 12.65 million meter cube. And now let's see how to find out the constant withdrawal rate, which is the objective of this question. So now step 1, step 2, step 3 are actually providing us several information about the various processes which are occurring in the reservoir system. So in the step 1 we saw what was the input volume, in the step 2 we saw what was the output volume, and in the step 3 we saw how there is a change in the volume within the reservoir. So we will be utilizing the information that we got from this step 1 to step 3 in finding the constant withdrawal rate in the step 4. So if we see, step 1 was the input to the system, so we are subtracting step 2, which was the output from the system, and step 3, which was the change in the storage volume, or more specifically it was the drop in the reservoir volume. So subtracting the output from the reservoir system and drop in the reservoir volume from the reservoir system from the total amount of water that was actually input to the reservoir system will provide us with the volume of the water which is actually being withdrawn from the reservoir system. So substituting these values which we obtained from step 1, 2 and 3, here the step 1 was 17.54 million meter cube. This was the input volume, and it is being subtracted from the output volume, which is 1.65 millimeter cube, and it is again subtracted by the drop in the reservoir volume. Here we see that the drop in the reservoir volume was already negative, so this minus will become plus, and if we solve, we get the total constant withdrawal volume as 28.54 millimeter cube. But since in the problem it was asked to find out the constant withdrawal rate, so we know that the duration of this particular condition was 30 days. So let's divide this total withdrawal volume by the 30 days, and here it is. And in order to get the constant withdrawal rate in the units of meter cube per second, we have multiplied these days or converted these days into seconds. And also we have replaced this million by 10 power 6. Solving this ratio, we get 11.01 meter cube per second as the constant withdrawal rate. And this is the answer for the part 1 of this problem, where our focus was to find out the constant withdrawal rate for the fall in the reservoir level of 92 centimeters. So this is the summary of whatever the processes that we have done. So firstly, we identified the precipitation volume, which came as 2.54 millimeter cube. Then we also estimated inflow volume, which came as 15 millimeter cube. So in the step 1, what we did was to find out, our objective was to find out the total input volume. So we added the precipitation volume and inflow volume. So this serial number 1 plus 2 yielded total input volume in the reservoir system, which came as 17.54 millimeter cube. In the next part, we estimated the seepage volume, which came as 0.34 millimeter cube. And then we estimated evaporation volume, which came as 1.31 millimeter cube. So if we add serial number 4 and 5, it provided the total output volume, which we have seen in step 2. So these 4 plus 5 actually yielded 1.65 millimeter cube of the total output volume from the reservoir system. In the next part, we estimated the drop in the reservoir volume, which came as minus 12.65 millimeter cube. Here minus sign is indicative of the fall in the reservoir volume. If there would have been increase in the reservoir volume, we would have been using plus sign instead of minus. In the next step, we estimated the withdrawal volume, and in order to find out the withdrawal volume, what we did is we subtracted serial number 6 and 7 from serial number 3. That is technically step 1 minus step 2 minus step 3, which yielded 28.54 millimeter cube as the total volume of water which is being withdrawn from the reservoir system. And in order to find out the rate, we just divided the total volume by the duration, and which was 30 days in the present condition, and finally we got the constant withdrawal rate of 11.01 meter cube per second. So I hope you were able to follow the first part of this problem, and the first part was the case of level drop by 92 centimeter. Likewise, I request all the viewers that you may please try to solve this problem by following the same logic and the steps which were actually explained for solving the part 2 of this problem, which is when the level drop is not 92 centimeter, it is 73 centimeter. So although I haven't provided the solution for the part 2, but here is the summary of the responses that you are going to get if you are going to solve the case 2 of this problem, where the level drop of the reservoir volume or reservoir depth is 73 centimeter. So if we look carefully, the drop in the reservoir volume is now minus 10.04 million meter cube, and the withdrawal volume will change to 25.93 millimeter cube. So if you solve this part, you will get the withdrawal rate of 10 meter cube per second. So to conclude, if the level drop is reduced, then the withdrawal rate is also reduced. So because we have seen in the previous slide that for the 92 centimeter drop, the withdrawal rate was 11 meter cube per second. So if we reduce the level drop from 92 centimeter to 73 centimeter, keeping all the other conditions same, then we find that the withdrawal rate is also decreasing and it becomes 10 meter cube per second. So in this way, you can also solve this problem for different level drops, or you can also solve problem for what if the level is not dropping but instead it is increasing. I hope you were able to follow both parts of this problem, and should you have any concerns or any doubts regarding how to solve these kind of problem or similar kind of problem, please feel free to reach out to me. You can drop your doubts in the comment section in this YouTube channel. Also, you can drop your concerns in the chat section of the NPTEL. I thank you for being the part of this series. This was the first part or the first session of the series of 12 lectures to be taken regarding the various aspects of surface water hydrology, and the focus will be to keep solving various numerical problems on each topic of the course. Thank you.